1965 was a successful year for space science and applications. There were the spectacular results of the Ranger and Mariner missions and the other significant accomplishments which advanced our programs toward their objectives. These objectives are to explore the moon, the planets, and the interplanetary environment of our solar system, to investigate the sun and its relationship to Earth, the geophysical properties of the Earth, and the physical nature of the universe, to determine the biological effects of the space environment on Earth life forms, and to search for and analyze extraterrestrial life, to develop experiments for manned space flights which use the special capabilities of the trained astronaut as a sensor, manipulator, and evaluator, to provide pre-doctoral training for scientists and engineers, and grants for space science research projects and laboratory facilities to best use university resources for the national space effort, to develop and manage launch vehicle systems on which reliable space transportation for all payloads depends, to conduct research and development on meteorological satellite systems and support the Weather Bureau in applying them to an operational system, to develop and apply space technology to other practical satellite applications, such as communication and navigation. In April 1965, one accomplishment in communications was the NASA turnover of SYNCOM-3 and SYNCOM-2 to the Department of Defense for their operational use. The basic engineering data planned for them had been largely collected. SYNCOM-3 was launched in 1964 and maneuvered into the world's first stationary orbit at an altitude of about 22,300 miles over the mid-Pacific. SYNCOM-2, launched into the world's first synchronous orbit in 1963, was moved in 1965 to a new station above the Indian Ocean. Now both communications satellites are serving the Department of Defense for voice and teletype to Southeast Asia. Experiments in air-to-ground communications by satellite were successfully conducted in January between a ground station and a Pan American Airways aircraft in flight over the Pacific. The two-way airborne terminal communicated via SYNCOM-3 with the California ground station from a position as far away as Hong Kong. And also in 1965, communications for Gemini manned space flights were routed through the SYNCOM-3 spacecraft. Early Bird, the first commercial communications satellite, was launched by NASA in April for the Communications Satellite Corporation on a reimbursable basis. The payload was a direct outgrowth of SYNCOM developments. The first Early Bird inaugurated live transatlantic programs in April. It also made possible the live television transmission of the Gemini 6 and Gemini 7 recoveries from aboard the carrier Wasp. This used the type of transportable ground station first developed for NASA's communications satellite program. In 1965, the first prototype model of an applications technology satellite was produced under the direction of Goddard Space Flight Center. This program is a major NASA effort in communications, navigation, and meteorology. It is concerned with the advanced technology of gravity gradient and spin-stabilized orientation systems. It will also be used for antenna research and the determination of environmental effects on components. Technology experiments for the first flights have been selected, and initial flight is scheduled for 1966. Most significant accomplishment of the meteorological program in 1965 was Tyros 9, which rolls through space like a cartwheel, taking weather pictures of the entire world each day. The Delta vehicle, used in launching Tyros 9, has successfully launched 31 satellites in 34 attempts. This includes a remarkable record of 22 successful launches in a row. Once in orbit, ground commands triggered the delicate turning maneuver which put Tyros 9 over on its side. Tyros 9 was put into a nearly polar orbit over the rotating Earth so that it can photograph the entire world each day. The satellite was programmed to take 400 pictures daily. Each day's coverage is converted to neph-analysis maps, which show the storm fronts all over the world. These are made available to weather forecasters for their analyses. The wheel configuration of Tyros 9 will be used in the series of operational satellites developed by NASA for the Weather Bureau. This system will be known as TOS. Some satellites will carry cameras for automatic picture transmission to small receiving stations all over the world. Others will carry an advanced Vidicon camera with tape storage to send back its global observations to the United States. In July, NASA launched Tyros 10 for the United States Weather Bureau. This latest Tyros joined Tyros 7, 8, and 9 in space and marked the first time that 4 weather satellites were operating simultaneously. In September, all 4 storm trackers photographed Hurricane Betsy, making it the best followed hurricane in history. Tyros 7 entered its 3rd year of operation, 4 times the expected lifetime for a weather satellite. Another use for Tyros was weather monitoring before and during the 8-day Gemini 5 manned spaceflight. Because of a Tyros-based forecast of impending storms in the recovery area, the mission was shortened by 1 orbit. Nimbus is now the focus of advanced research and development in the meteorological program. Work on the 2nd flight model continued throughout 1965 under the direction of Goddard Space Flight Center. Scheduled for launching in 1966, Nimbus will carry both daytime and nighttime camera systems. An attractive feature of the next Nimbus will be the ability of small, relatively inexpensive ground stations to receive live pictures during the daytime as well as infrared pictures at night. 1965 has seen notable accomplishments in the lunar and planetary programs. These include the completion of the successful Mariner mission to Mars, the first flight of the new Pioneer series of interplanetary missions, and the success of the last 2 Ranger photographic missions to the Moon. The extraordinary pictures sent back from the successful Ranger 7 mission caused substantial modifications in earlier theories about the Moon. They resulted in lunar maps and models of an accuracy and scale to within a few feet. The area within the sea of clouds which Ranger 7 photographed was renamed Mare Cognitum, the known sea. Ranger 8 target areas were re-evaluated according to Ranger 7 findings. It was launched in February from Cape Kennedy by an Atlas Agena. The Agena has provided NASA with a versatile vehicle system. Since the beginning of 1964, 10 out of 11 launches were successful. The Ranger 8 mission achieved its objectives. Not the least of these was the further qualification of the sophisticated and highly accurate guidance and command systems, and of camera technology. These systems performed at their peak when Ranger 9 was launched successfully in March. As it approached the Moon, it sent back from its 6 cameras more than 5,800 pictures of the lunar surface. Here is a speeded-up sample. Ranger 9 marked the completion of the successful program managed by Jet Propulsion Laboratory for NASA. We have learned a great deal from this program about the topography of several lunar areas. For example, we know that the lunar surface within a crater like Alphonsus is remarkably similar to the surface of Mare Tranquillitatis and Mare Cognitum, photographed by earlier Rangers. If firm enough, these surfaces may be suitable for the landing of the unmanned Surveyor and the manned Lunar Excursion Module. The dark halos around the small craters in Alphonsus suggest past or present volcanic activity. The spectacular final photos of the Ranger 9 approach to Alphonsus were seen live on television by millions of Americans as they were taken. They had a resolution of better than 1 foot just before Ranger 9 impacted, within a mile of the target. Continuing study of the Moon's topography will be accomplished by Lunar Orbiter. In 1965, a prototype model was completed and began testing. First Lunar Orbiter flight is scheduled for 1966, using an Atlas Agena D launch vehicle. Photographic reconnaissance will be its prime task, and there is considerable flexibility in the way the photographs can be tied together. Last year, 10 potential areas were selected for coverage by the first mission. They include examples of all the major types of the Moon's surface to permit assessment of their suitability for spacecraft landings. Each is 22 miles wide and 58 miles long. 9 of the 10 sites are within the area proposed for Apollo manned landings. Lunar Orbiter will approach within 29 miles of the lunar surface at perigee and may remain in orbit for up to 1 year. This should make it an ideal vehicle to obtain scientific data as well as extensive photographic coverage. The end of the year saw the first flight model of Surveyor in final system test prior to shipment to Cape Kennedy. Surveyor is our most complex unmanned lunar exploration project. It is designed to make a soft landing on the Moon and provide a wide variety of scientific data, as well as to survey areas on the lunar surface as possible landing sites for manned missions. This flight model Surveyor and the prototype which preceded it underwent qualification testing throughout 1965 under the management of the Jet Propulsion Laboratory. The spacecraft was subjected to vibration tests. It went into a simulated space environment in the solar thermal vacuum chamber. With its ground support equipment, the prototype was shipped to Cape Kennedy. Here, it was used to check out launch facilities and procedures. Then it moved to Goldstone Tracking Station in the California desert. Here, it underwent compatibility testing with NASA's Deep Space Network. On November 22nd, a most significant milestone was passed in the Surveyor program. A T-2N terminal descent test vehicle performed successfully in a combined tether and descent test at Holloman Air Force Base, New Mexico. Prime objectives were to verify the soft landing capabilities of the Surveyor spacecraft and evaluate critical flight parameters in the velocity sensor, flight control, and vernier engine subsystems. You will note that once the vehicle was released from the balloon, there was no discernible displacement in pitch, yaw, or roll. This stable descent attitude was maintained by the constantly varying thrust output of the throttle-controlled engines, responding to the commands of the flight control subsystem. After release, the vehicle automatically adjusted to the planned descent trajectory until a constant descent rate of 5 feet per second was reached. This constant descent rate can be seen as the time when the stabilizing chute fell to the side of the vehicle. In effect, the spacecraft made a simulated lunar surface landing and was recovered by parachute at an altitude of 500 feet. From this first successful performance of the model, we can conclude that the design is adequate to guide the spacecraft to a gentle landing on the Moon. The system will, however, undergo further testing. Many problems, managerial and technical, were overcome during this year of qualification and test. Now, a Surveyor spacecraft is nearing flight acceptance for the first mission in the most difficult project yet undertaken in the Space Science and Applications program. Centaur, launch vehicle for Surveyor, has completed the first phase of its development program with a successful launch in August, carrying a Surveyor dynamic test model. Sun Tower is now fully qualified to meet Surveyor direct descent requirements. The two-burn development phase to put Surveyor into parking orbit should be completed late in 1966.